Hello, everyone. We'll get started in just a moment here. All right. Hi, everyone. Thank you so much for joining us today for this webinar series. This is the final webinar in a series of 4 webinars that's been hosted by the AGU Hydrology Section Student Subcommittee, or AGU H3S, in our annual webinar series, Navigating Academic Waters. Before I hand things off to our speakers for today, I wanted to give a brief overview of CUAHSI while folks are still getting logged on and getting settled. My name is Julia Masterman. My pronouns are she, her, and I'm the training coordinator with CUAHSI. CUAHSI is the Consortium of Universities for the Advancement of Hydrologic Science, and we're a nonprofit organization funded in part by the National Science Foundation. Our mission is to empower the water community in advanced science through collaboration, infrastructure, and education. CUAHSI sustains infrastructure to enable research and collaboration. This includes a data repository for water science data called HydroShare. By providing this support and infrastructure, CUAHSI can help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies. We also provide educational opportunities and infrastructure for student support. These include workshops, a summer institute for graduate students, webinar series and events like this one, a virtual university, and more. Both our data infrastructure and educational opportunities are designed to enable collaboration and interdisciplinary work. There's a few upcoming deadlines I want to point folks towards. Firstly, next week, we'll be hosting another webinar titled Post-Field Season Data Practices for Research Success. This is a follow-up to a webinar we did in the spring with advice on how to prepare for a field season from a data perspective. We will hear from Lindsay Platt, who happens to also be a speaker on today's webinar, as well as Amber Bogan, another data scientist at CUAHSI. So consider joining us for tips and advice, how to be good data stewards and get the most utility from the data you and your colleagues worked so hard to gather this past field season. I also want to highlight that applications for fellows for the Water Prediction Innovators Summer Institute will be opening very soon. The Summer Institute is a partnership between CUAHSI and the University of Alabama that aims to engage the academic community in research to advance water prediction. As I mentioned, the call for graduate student fellows will be opening in the coming weeks, very soon. And the call for theme leaders who mentor graduate students, student research teams over the summer, the call for that is open now and applications they will start reviewing applications December 1st. If you have any questions about this program, please feel free to reach out to me directly via email. The Summer Institute fellows work on projects relating to water prediction and flood forecasting for 7 weeks over the summer. Graduate students work in small teams, and we're always blown away by the quality of work that comes out of these 7 short weeks and the impact that the program has on the career of its participants. So we're looking forward to another great Summer Institute next summer. And with that, I'd encourage you to connect with CUAHSI. You can join our mailing list, the QR code on this page, or I'm going to put a link in the chat in a moment, and follow us on social media. And you can also find us at conferences, including this year's AGU. We'll be in the exhibit hall alongside AGU H3S at booth 836. Please feel free to come by and say hi. All right, as mentioned before, this webinar is a part of a 4-part series. Recordings for the previous webinars are on the CUAHSI YouTube channel, as will the recording for today's webinar will also be posted on the CUAHSI YouTube channel. All right, so today's webinar is on leveraging AI and data science in hydrology. A huge thank you to our speakers for taking the time to join us today, and a major kudos to the hosts at AGU H3S for convening such a wonderful panel. A few logistics. We ask that you use the Q&A functionality to submit questions to our speakers. Please feel to add any questions at any time. We hope that this is a conversation with you, the audience. And you're also able to upvote any that are especially of interest to you. We'll do our best to get to as many as possible. And we expect that all involved with CUAHSI Cyber Seminars uphold the CUAHSI Code of Conduct and promote and maintain a professional, considerate, respectful virtual environment. And with that, I will pass the mic on to our conveners to give a brief overview of AGU H3S and kick off this webinar. Thanks so much.
Thank you so much, Julia. Hi, everyone. I'm Sujana, and I would like to welcome all of you to this final webinar of the Navigating Academic Water series. We're very excited to have you all here. Right now, my screen shows that we have more than 100 participants, which is very exciting. Thank you so much for taking your time to be here today and to listen to these wonderful panelists that we have here. Before we get started, just giving you a brief explanation of what AGU S3S is. So S3S, it's the AGU's Hydrology Student Section Subcommittee, and we are a group of motivated students and early career scientists. We are also one of the very active student subcommittees of AGU, who work together to provide students and early career hydrologists with opportunities for networking, professional development, and social interactions. We organize different webinars, river cups, catchment cups. We also do town halls at AGU as well. You can find our more information in our website, which is agu-s3s.org. If you have any questions about like what we do or how we operate, you can come find us in the AGU exhibition hall at booth 836, and you can also like email us. Right now, we are about to open new applications for our membership for next year. So if you are interested to join us as a member, feel free to check our websites or visit us at the AGU booth, and then feel free to apply. So today we are two people from S3S who will be facilitating this webinar. I am Sujana Timilsina, a PhD candidate at the University of Texas at Austin, and I'm also the chair-elect for AGU S3S this year. And we also have Ashleigh.
Yeah, so I'm Ashleigh Kirker. I'm a new assistant professor at Virginia Tech, and I'm really excited to get this panel started. So without any further ado, I'm going to introduce our three panelists and ask them a question to kind of get the collaborative discussion juices flowing. So we'll just go alphabetically. First, we have Admin Husic, who's an associate professor of civil and environmental engineering here at Virginia Tech. His team works to advance our understanding of the connectivity of water, sediment, and nutrients in human disturbed landscapes, and he leverages aquatic sensing, geochemical tracing, deep learning, and explainable artificial intelligence to solve problems and ensure equitable access to water. We're also joined by Dr. Paul Liu. He's a full professor in the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University, and he serves as the Director of International Affairs for the College of Sciences there. He recently taught a graduate level course titled Generative AI for Science, and he serves on the NSA North Carolina State AI Strategy Advising Group, and he also co-founded Ocean AI and Ocean GPT. And finally, we are joined by Lindsay Platt, who is an environmental data scientist at CUAHSI and is currently the lead of operations. At CUAHSI, Lindsay applies data science techniques to support business operations and interdisciplinary research. Her career focuses on supporting computational hydrology through constructing reproducible data pipelines, harmonizing large data sets, and advancing data fluency. So because this is a group of people who are really knowledgeable about data science and about hydrology, I think a great question to get started with would be, why should a hydrologist, especially given our early career audience, why should a hydrologist learn data science? And maybe we'll just, does anyone want to get started, or I can call on you?
I can jump in.
Awesome.
Ashleigh.
Go ahead.
Yes. So, yeah, thank you, H3S, for hosting this a really great webinar. Before we start, I do want to mention that we originally had another panelist, Jake Zwart from the United States Geological Survey, but because of the shutdown, he was not able to come. So I want to recognize that that's a valuable contribution, to this discussion that we're not able to have. So hopefully the shutdown doesn't last too much longer, and the USGS and others can continue to contribute to the great science. Because the data that they provide, much of what we're able to do in data science with respect to hydrology is because of the incredible data that the USGS and the EPA and Forest Service and USDA and other agencies provide. So I do want to say that from the start. So why should a hydrologist learn data science? I think data science is an important skill for hydrologists because you want to use the tools at your disposal. You know, data science in its current shape with machine learning is providing us an ability to do things that we either couldn't do in the past or we weren't satisfied with the performance of previous tools. So maybe 50 years ago, you would have used a regression model to predict stream flow or a simple conceptual bucket model. And then 30 years ago, you have physics-based or fully distributed models where you're solving equations. And that has advantages, but it also has some weaknesses. And now we are in a period where we have generated more data, sometimes more than we know what to do with. And this data can be enabled to overcome existing limitations, to make stronger predictions, to forecast with higher accuracy, and for those improved forecasts to then be put into place for some kind of management or mitigation or a risk avoidance scenario. So I think hydrologists should learn data science because it is a tool that helps us achieve things we care about.
Yeah, maybe I can start. First of all, thank you very much to have me here today. It's so amazing. I mean, your graduate student or earlier career scientist, geoscientist organize this wonderful webinar series. I think many graduate students, our postdoc, this community will benefit from this dialogue. So as Admin mentioned, we are in a stage of we have so massive and vast amount of data available. The data not only, if you look at it back to 50 or 60 years ago, we mainly based on gauged stationary data. But now, not only stationary data, but more dimensional data from the air, from the remote sensing, from Landsat, from MOSAT, from Centennial, and all the way from surface flow and groundwater flow. No, it's a multi-dimension, not only one-time series, multi-time series, multivariant data available now. So in order to take advantage of the machine learning or even the hardware, the GPU available, the computational power, we really need to understand the data. So understand the data needs us more knowledge combined, not only geoscience, hydrology, but from the data itself. That's the basic receive. We really in a new stage cross-section need our geoscientist or young career student have a good understanding, good knowledge training in data science or statistics at least.
Yeah, and I've been thinking about like what is the definition of data science? and really when I think about it and talk about it, I think about how data science is about gaining insights from data, which is exactly what hydrologists are doing all the time, is gaining insights from their water data. The data science is required because of the volume of data that we have now. We can't rely on our traditional approaches. And because of the volume of data and the kind of popularity of AI, I think people are going to use water data, try to make predictions and do forecasting in AI, whether or not they have the hydrology experience. So it's super important that people with the hydrology background join this discipline of computational hydrology and data science and hydrology to make sure that kind of field and discipline grounding is represented, because if not, people are going to misuse and misinterpret some of the things that are coming out of our AI models.
Thank you. I think that was a very good explanation of why we need to learn data science. Also, I feel like in addition to that questions, I think will always be a question for a fresh starter, what key skills do we need, right? If I want to start right now in this field, so what are the key skills that are needed to apply like AI or machine learning, or even like get like familiar with the field of data science for like hydrology?
Yeah, I think about this frequently because of the interactions I have with students through CUAHSI is, we do a lot of kind of training things. Previously, when I was at the US Geological Survey as a data scientist, I also helped with our training too. And I mean, I think foundationally, hydrologists need more coding and data wrangling skills to be able to quickly pull together data sets that they want to use, try out different models. It's just having a foundation in data processing and wrangling with code is kind of the like underlying thing that you need to be able to pick up a new like Python model or something and apply it. And then the other thing that I was thinking about, just kind of going off of what I was saying in the first question, is a strong knowledge of hydrology is really important so that you can critically evaluate what's coming out of your models. Because without that, you could trust things that are coming out when you probably shouldn't.
Yeah, I want to echo what Lindsay said there about having that strong foundational knowledge in hydrology allows you to critique and to be skeptical about the model. I think that is, it's a skill that you can learn in any class, is to question the data, to be skeptical about the model result, to not just assume the model does well because it gets a high score in some model evaluation metric. In terms of, skills, courses, an understanding of calculus, linear algebra, statistics, uncertainty, these are, parallel to your understanding of hydrology. And when you put these two together, then I think you can really like know what you're doing and have a responsible use of the tools, so that if you were to hand over your prediction to someone, you know the limitations and you're able to describe those, whether it's to a public works agency or for flood forecasting, whatever it might be. That's really important. I started a class here at Virginia Tech this past spring on water resources, machine learning and water resources. And more than teaching tools or coding or models, I try to instill in the students like this idea that you always want to kind of think about how you might break the model, right? Not to get the model to work, but to get it to not work. If all you have to do is change one tiny little thing and your model totally falls apart, it's not a strong model. It needs to be robust to perturbations. So that kind of like critical thinking and skepticism and curiosity, those things go a long way, much more than just knowing how to code or just knowing how to calculate a water balance. Having that critical appraisal of your modeling approach and the results is really important for responsible use of machine learning.
Yes, I totally agree, Admin and Lindsay, what they said. First of all, as a geoscientist, particularly in hydrology field, we really need a basic training, a well understanding of the domain knowledge. So, I mean, this is actually one of our advantage compare the computer science graduate student or even data science statistics department field, the graduate student, because with this kind of understanding and this kind of a basic scientific training, when we handle the data, as we all agree, now is a massive, so many data available, but unfortunately, the so many data is not clean. The data is not ready to use. So anybody who tried to pre-train a model, we understand 80 to 90% of the time we spend is to preparing the data. Preparing the data costs much more amount of time. But not only computer scaling, write a couple line of code to clean the data. No, we have to have that kind of knowledge. When we look at the data, is this the data is abnormal, particularly that strange data point? Is this represent an event? Or this is something from our instrument sensor, some problem? That kind of knowledge is very critical, very important for us to have. But by saying that, we still need to practice. So I suggest, many graduate students, you can pick up a very simple machine learning model, starting from simple one. You don't need to go to a deep learning one. Yeah, simple, even one-dimensional, even not need to do a diffusion model. Let's pick up a one-dimensional CNN model and prepare a clean small set of data, and then how to feed in the model, how to adjust the model parameters, so how to see the accuracy or even error. So that's a practice will gradually to equip you to in this field. You can combine your knowledge of hydrology and also your coding. But there's a couple more things beyond the hydrology. The Python code or R code is the geospatial analysis. We all know GIS is very, very important. So with this kind of a combination with the traditional physical or process driving method, now with the machine learning, so this can give you an edge, in this field. So I think this is some skill we really have, need the combination. As soon as you have this combination, you will be very good, in this age.
Thank you all. I really appreciate how everyone sort of hit on this idea that a deep domain knowledge is really important for developing. I've been calling it like a data sniff test of like, does this make sense? Does this not make sense? And I think it's one of the most kind of valuable skills you can develop throughout your kind of grad school career. But several of you also talked about the issue of data wrangling, cleaning data. And so I was wondering if anyone had any insight on like rules of thumb, best practices for when we can, I don't know, gap filling time series, harmonizing data to get it ready for a model. How do you go about that?
Oh, maybe I can start. When we talk about hydrology, as we mentioned back to 1950, 1960, we heavily rely on station or gauge the data. So sometimes with the time series, gauge the point source. So that's the relatively one dimension and easy process. But now, it's particularly with the satellite, with the remote sensing, with more even model generated data available, how we can convert from that point source station gauge oriented to a two-dimension distributed spatial and temporal distributed 3D view of the data, how we can incorporate them together. And for example, if we try to predict a flooding, how we can combine the high resolution, precipitation, evaporation, surface flow, soil moisture, all that kind of parameter into that machine learning model. And that's need a lot of knowledge, understand their relationship or what's the weight. Because if you understand a little bit of the generative AI, particular large language model, the training process is doing the weight. Each token, how much the weight, how much the dimension, that's the field. So in terms of hydrology, how we can plot evaporation with like a soil moisture, like underground groundwater, water table, or the river discharge, or even flooding process combined together. This is kind of the challenge. Particularly now, we have how we can downgrade the global climate model to a specific regional oriented data as an input. This is another level, of the change. And sometimes the data itself is not scientifically how to say, cleaned or unified, even use a different international metrics or American, unit, like a different temperature, different length, weight. I mean, this is one of the challenge, but also sometimes it's a community or citizen reported the data, social media full of the data, full of the snapshot, the pictures, or even reported data. How we can incorporate those kind of data in our AI-driven, particularly the risk time-sensitive response. This is all the challenge we are facing now. So with this kind of knowledge or experience or training will be very critical for the next generation hydrologist.
Thank you. Lindsay, did you want to speak to that? It looked like you had unmuted.
Well, yeah, I was just thinking about some of the like bottlenecks that you might run into in these situations. Paul was talking a lot about like the different types of data and formats, and another element of that is like those are all coming from different sources, which then you have to learn the access patterns for all of those, which can be challenging to kind of pull it all together. One thing I just wanted to like make a plug for, which is kind of like the passion that I have throughout all of my projects that I work on, is thinking about reproducibility in our science, because somebody has probably published a paper using a model or something that you want to pick up, but did they also publish the code that went into cleaning their data and getting it ready for that model? Because if they did, then you could kind of pick that up and start from there and build on top of that. And then we're kind of slowly over time, if we're all doing that, helping get people past some of those initial data bottlenecks, or even maybe you didn't think about gap filling originally and like what the different possible ways you could gap fill your data are. But if somebody had published the code behind their data pre-processing, you could lean on that and say, oh, they did this for their gap filling. And I think that matches the approach that I should take with my data here. So just a shout out PSA for sharing all of this code that we're all spending so much time writing. I think you said 80 to 90% of our time is on the data pre-processing, but we all sunk a ton of time into making that happen, and we should be sharing it so that others can build on top of that. That's my PSA for the day, my soapbox moment.
Yeah, and also to bring this back to the domain knowledge, to have data, to have good data. If you want good model predictions, you need to put in good data. But to even understand what good data are, you have to have the domain knowledge. So I'll give like two examples. One is, when I first started as a student, I did a lot of field work with sensors. And they're fantastic because they give you a ton of data, much more than if you went out physically and collected a sample and analyzed it in the lab. So that part's fantastic. But sensors are not perfect. Okay, you can have a buildup of sediment on the viewing window of the sensor, and you get wild results. You can have spikes and drift over time, all of these things. But unless you know that, unless you have that domain knowledge, you will be trying to fit a model to something that is just noise or erroneous data. So you need to have that knowledge about your data, because even if it passes certain, statistical tests, those may not catch the underlying issues. Okay, that's the first thing. The second thing is I had a student create a model of stream flow at many sites, and it worked really well for most sites. As it's a kind of deep learning model called a long short-term memory network, and it worked great at most sites. But there were a few sites where it was awful at. And I asked the student, show me the time series of your prediction versus your observation. And at one of the sites where it was doing poorly, the stream flow would be like 1,000 CFS exactly for 10 days in a row. Then it would drop down to 500 CFS for 5 days in a row. Then it would go up to 2,000 CFS, and it would be constant jumps. And the student didn't know about reservoir operations. Okay, so they were fitting this like terrestrial rainfall runoff model, but not accounting for the fact that there is this huge storage reservoir that there's nothing in the inputs in the neural network that reflects the operations of the reservoir. So there's no way that pattern can be learned. And if 95% of your sites are not regulated, but 5% are, your model doesn't have enough data to learn about flow regulation. Okay, so you need to think about that before you even run the model, before you clean the data on the site selection side of things. So again, domain expertise to me is, I don't want to say anything is more important than anything else, but it is something that you can't just do the data science. You have to have the domain expertise to enable your data science to do more than what you could do if you just skipped to running, Python codes off the shelf.
Thank you so much. That I think was very helpful, especially like when you're trying to choose between like models as well. And that our next question from our audience as well. I think we have questions related to how do you choose an AI or machine learning model? Like, do you use what you learned before and willing to learn new models? Or like, I think some of our audience are curious about like how to choose the machine learning or AI models.
I think you can choose the model that, like, choose the tool for the job. If a simple linear regression gives you like really great results, there's no reason to create, a neural network. If you can do something with a simple model, you don't need a complex model. So that would be my first suggestion, is start simple. There have been many comparisons of different modeling approaches, purely machine learning modeling, like comparing a random forest to a CNN to an LSTM. And what you see is oftentimes like there are differences, but they're pretty marginal. Okay, so I'd say choose the tool for the job that has the interpretability. If you want interpretability, some models are easier to interpret than others. So there's that balance. I would focus more on choosing the right model for the job and starting simpler rather than trying every model variety to make a, R squared improvement by, 0.01 or 0.02. I would spend more time on interpreting the results than marginally improving model performance by trying a bunch of different models.
So I also echo Adam's say, if some case, some scenario, you can use the traditional physical driving model. You do not need to have to use the numerical model. So, but at the same time, for the student, if you want to really come into the machine learning AI-driven hydraulic modeling field, so I would suggest pick up a simple one first. For example, the long-term, short-term memory model. That's the time series, very simple one, very easy. Maybe within 50 lines of code, you can do a very simple model. But this drive you understand how the neural network works. So from that point view, but you have to understand the physics, because many beginning the earlier phase, simple machine learning model, there's no physical processing involved. So this is dangerous. You can make the observation or predict data looks beautiful, but if what's the driving, what's the physical, what's the energy or mass balance behind? Is any parameter driving there? No. So that's the thing from the beginning. Then gradually understand what's the the domain knowledge. And then if possible, because this is the trend, if we look at the most recent publication, 24 and 25 last year and this year, there's a couple people already talk about, or model even available, how we can use a hybrid physical and machine learning model combined to get a best result. Because the machine learning, the AI, the good thing is quick. For example, the global weather forecast, you can use just 1 minute, use a graph cast to get next 10 days forecast. So unfortunately, in the hydrology, this just started. How we can apply that kind of advantage, because the faster we want to do using a couple minutes, we can predict the flooding risk warning. So this is what we want to do. But we have to combine the physical process and the machine learning knowledge combined. I know this is a challenge, but this is the mindset we have to keep in mind.
I think that's a really helpful thing to think about, and understanding that like simple models are an option, right? You don't have to go for the most complex or the absolute best R squared. Interpretability is important. Reproducibility, to like rejoin Lindsay on her soapbox, is really important. And so I'm seeing a couple of questions from the audience about data availability and resolution, and folks are having challenges with that. And so maybe this is sort of a two-pronged question, which is, first, how do you deal with data availability issues? Have you found any data sets that you find are like really helpful for supporting your work? And then on the other end, how do we be good stewards of our data and support other scientists who might want to use that data going forward? I'm gonna call on Lindsay because you didn't get to answer the last question.
Sorry, I'm just like reading that question that you were referring to. Yeah. I mean, I think in terms of like long-term data and long-term reliable data, I mean, kind of talked about this at the beginning, the federal data sets are kind of the go-to for that, because they have funding and support most of the time to operate, and there's like teams of people behind data quality assurance and control, and not a lot of downtime, really great documentation and access for them. So those are usually like my go-to, and they're improving resolution all the time. So you can get data at 15-minute resolution for a lot of places. Some of them are adding additional sensors that are even more fine than that. So that's kind of like the thing that probably biases me, is I use that data all the time, and I feel like sometimes I may build my research questions around knowing that data exists, which is definitely a limitation. In terms of the like how to help make sure that we're being good stewards when we have data we've collected, say, and want to make sure other people can use it and share it. One of the biggest challenges with pulling data together from different sources is just the variability in how people describe that data and the metadata that they provide with it. So at the beginning, Julia made a shout out to HydroShare, which is CUAHSI's data publishing portal and ecosystem. And it's a place for people to publish their data. And there's a lot of individual user control over what goes along with that data that you're publishing. And so one thing we all need to be just better about is taking the time, even though it does take a lot of time, to describe exactly what that data is, make sure that you're talking about what units are used in it, talking about the quality and noting some, maybe if it was field sensor data, like some issues, and just describing it as fully as possible, even though you've been in this situation, you're like at the end of your project and you're like, I just need to get this up there and out and be done with this and move on. But then it becomes more difficult for somebody to take that and say, increase the resolution of data that they're using for some other project, because they can't truly use what you've published because there's missing information about it. So yeah, that's like it's boring, but taking the time to like make good metadata about the data you're publishing is just so important. And it's important that we plan the time into doing that, and not rush it at the end.
as Lindsay earlier mentioned, sometimes we try to duplicate when we read a publication. Oh, we get very excited. Oh, this is wonderful. This is the source code they published. But when you really dig in, most of the time you found the code doesn't work. And this not work as you expected because it's not the code has a bug, but mainly it's the data processing process, sometimes not published. And maybe they tell you, download this Centennial or Landsat data from European Space Center website. And where you choose the data after you download that, how you correct the data, how you calibrate the data, how you clean the data. That's the challenge. So I would suggest that maybe we have a good practice when we publish something. We have that GitHub website, also have a detailing how to process the data. This, I think, very, very useful. And for example, when we download so many remote sensing data, the cloud, how you remove the cloud, how you meet your need, and to have that kind of moisture landscape or land cover, parameters involved. I mean, that's also a part of the challenge. But there's a lot of tool available for us. I hope the young generation can also have that kind of a good practice. We can share the tool we used or the code we used to get the data ready. As soon as the data ready, and this is my experience, also my student experience. When you get this ready, when you click and run the publisher code, if successful, you have a very good confidence. If not successful, if you cannot figure out within 1 week, most of the time you give up because you feel frustrated. You cannot figure out what's going on. So, I mean, this is somehow in the classroom, as I mentioned in the beginning, I mentioned last fall, I teach a graduate student course, Generative AI for Science. So each class module, I include a Google Colab code. So the student can just click and run. And then I encourage them modify my code. So they can have the original workable code available, sample code available. They can click, they can see the result. For example, the shoreline change, or for example, land cover prediction. When they able to download the data, process the data, and run the model and see the prediction, they feel very happy. They are real comfortable to modify the location, from my code to their specific location, all the different resolution or different how many route, itinerary you train. So I think even to a faculty, this is also a challenge. We want to, particularly in this new age of the AI, we want to encourage more people in this field by providing completely code or our workflow. So I hope the young people also have a good practice like this.
Thank you. I think we do have a lot of questions now from our audience, and I would like to say that, we're trying to combine the questions so that we are able to answer like many questions at the same time. The next question that we have here is about the common mistakes or limitations or pitfalls that are important to be aware of for researchers with a hydrology background who are just getting started with AI or machine learning.
Let's see. I would say this kind of builds off of something I said earlier, but I think one common mistake is just the pursuit of just higher evaluation metrics. That's, to me, one common mistake. And I think that fixation can sometimes get people to be reticent or shy about revealing their model's weaknesses. So I think being open about where your model doesn't work, having that mindset going in can be really informative because that sets the stage for where improvements can be made. For example, one of my students had a publication in a water resources research that came out a few months ago. We built this LSTM model for predicting nitrate, and we used sensors, and it was awesome. We got great performance. in temporal forecasting. But then in prediction in ungauged basins, the model is actually pretty bad. And, we could have hidden that, but it went in the abstract. Like, this is, doesn't work in these scenarios. These are the things we can do to improve the model in those scenarios. So I think being transparent about your approach and methodology and not being worried or fearful if something doesn't work, if it can be used to motivate future improvements and progress. So don't always fixate on the highest score. Sometimes where the model doesn't work is more interesting than where it does.
So one thing I want to add is, try to understand the code, what the codes do for you. And because now everybody we are using ChatGPT, Cloud Coder, we like AI debugging for us, or even generate code or function for us. That's nothing wrong. That's good. But for a hydrologist, without a strong programming or coding experience, I would strongly suggest be very careful. Sometime maybe you throw to the ChatGPT or Cloud or Gemini, maybe come out something, if you hit it wrong, it works, the result looks beautiful, and you say, oh, hallelujah, that's it. But be very careful and pay attention. And this is I, in the class, ask a student, explain the code for me. Not only show me the result, but it's okay you use the AI help you debugging or you create the function, but you have to understand what that function doing, how many loops, what assumption inside. Maybe there's a trick or shortcut you never realized there, give you a good prediction, very good fit, but physically doesn't make sense. So that's something slowly. I know it's not easy, particularly without too much computer science background, but this is a new world. If you really want to use AI in hydrology, starting from the simple Python code, slowly, step by step, you can do it. So as myself, as a perfect example, I'm also coastal geologist, but I was maintaining the last 4 or 5 years from the general coding, use MATLAB, use Python. Gradually, I can fine-tune a model, even create a small large language model, even teaching a course. But I keep learning every day. So we can talk about later, but this is the important. Pay attention to what the code doing. Don't only look at the result.
There's a few questions from our audience in kind of the general sphere of uncertainty and maybe some concerns about AI models doing a great job of fitting the data, but maybe having limited ability to handle extremes or predictions. So could you speak a little bit about how to communicate that uncertainty and how to use these to the best of your ability without kind of falling prey to any of those pitfalls?
I would say there are at least 2 ways, and then Paul and Lindsay, you all can add to this, but I think there are 2 ways to address the problem of potentially overfitting to the data that you have. One of them is if you can get a data set that has a lot of variety, that's high quality data that has a lot of variety. So the model is able to see many instances. If you're predicting stream flow, for example, if you have 500 catchments, like the Camel's data set, they're primarily forested. So if you try to apply that model to an urban watershed, it probably, it might work, but it also might not. You would want to use a model that was trained and saw that kind of data. And the more variety you have, your model will become a little bit more robust. Ideally, that's the thought, is that it will learn more patterns that are associated with different kinds of inputs. That's thing number one. Thing number two, and this is very difficult, when you are trying, machine learning models learn from patterns that appear frequently enough in the data that the model can map those inputs to your output. The problem with extreme events is, by definition, they don't occur frequently. Okay, and but that is what deep learning models rely on. So This is something called saturation, when you try to predict at limits outside of what your model has seen or been trained on. To deal with that, one thing that can help is, like what Paul said earlier, is you can blend the process-based and the machine learning approaches. Like there's process-based, process-informed machine learning or differentiable modeling. These are ways where you can bake in a structural backbone that's process-based, but allow the model to learn some things you're not that certain about. So you balance those two things where you can hopefully overcome what doesn't appear in the data often because you know some process-informed rule that you can impose, even though you don't see it a lot in the data because of its rarity. So you need the tool for the job. That's kind of something that I come back to, is if I'm predicting extreme events, you need the right tool for that. If you're predicting, mean daily flow and you have pretty typical conditions, you need a different tool for that.
So the event driving, prediction is definitely the challenge for the geoscience field. And because there's not only one input or one parameter, or you can simply just come out that kind of event prediction is very difficult, like a flooding. So sometimes it's not a simple rainfall or precipitation. So this is back to earlier discussion. We need a kind of multi-variant of the data, process or combined, and also have a good model combined with the physical input neural network. They call it, physical is the PINN, instead of the CNN, DNA, or GNN. So with that physical process input, and then with the multi-data available, this will be enhance our capacity for this kind of event prediction. Definitely need a multi-variant data. And I mean, that's a challenge because more data you involved, the more you have to process the data, understand how much weight they play in the network hydraulic process. But that's definitely the direction. I maybe suggest a couple paper, for example, in 2021, greeneering, if you this field, that the paper talk about what role does the hydrologic science played in the age of the machine science. So, and also even this year, Penn State, the group of Penn State, Husic, that group in the in Nature Communication, talk about the, use the machine learning model, try to understand the role of evaporation, soil, the global scale hydrology shifting historically. So yeah, read that couple that kind of milestone paper.
Yeah, I would echo that definitely keep reading. Now, ChatGPT can, and other generative AI models, they can create a lot of stuff for you. But unless you read and you understand ahead of time, you can be led astray and waste your time and create models that are, had you done some reading or understood the background a little bit, you could have saved yourself a big headache. So reading is incredibly important. It's the most important part, I would say, of being an academic, is reading the literature. Every scientific paper represents the collective effort of many people, hundreds or thousands of hours, and they've conveniently condensed it to you in 10 pages, So you take advantage of that. Don't repeat 100 hours of headaches. Read the literature. You will do yourself a favor. And there's a great question. I know you all are the ones leading the questions, but one I want to make sure we get to because we don't have a lot of time. But there's one about for practitioners, managers, and administrators we're working with early academics. Maybe you were going to ask that one, Ashleigh. I saw you nodding.
That was my next one because I do
Okay,
think it's a
go
really
ahead, yeah.
well-worded question, but you're welcome to go along.
Okay, sure. So for practitioners, managers, and administrators working with early academics who may or may not be familiar with our water systems, such as reservoirs and water level management, how can we improve collaborative projects? What can we do on our end to prevent months of whoopsies and help our academic partners better understand the assignment? How can we be better communicators? How can we ask better questions that illuminate hangups and spark critical thinking without aggravating egos? Okay, that's a great question. Yeah. You always leave your ego at the door when you're collaborating. Everybody has something to learn from someone else. I think, without knowing the specific details here from anonymous attendee, I would say understand what your goals are. The early academic might in their head be trying to create a model that does something that is different from what you were hoping for. Or they might be trying to model something for which there is no adequate input data. So for example, I'll go back to the earlier example I said that's also, relevant to the reservoirs is when we were modeling stream flow in regulated rivers, we don't have hourly reservoir operation data at the CONUS scale. That just doesn't exist. So if we're trying to model stream flow in those systems, we just don't have the input data to be able to inform that. So you can have months of whoopsies and banging your head against a wall and talking past one another if you think you can achieve something that is just not presently possible with the data that's available. And that goes, if I could also answer a question from like 30 minutes ago by Danica about issues with data availability. I think to some extent data availability defines, not entirely, but it informs the scope of the questions you can ask. For example, I'm interested in reconstructing the historical record of sediment transport, of nutrient transport. If my historical, fertilizer application or rainfall data only go back to 1985, well, that's kind of the starting point of any trends I can do, right? I can't go back before then if I don't have the input data. So I define my questions to be answerable with the data that are available.
Mhm.
Okay.
So I almost, in the end, I want to add, also echo the admin's point. I think communication is also other key. Beside our domain knowledge, hydrology, our programming coding capacity. So communication to the policymaker, management department, even the local citizen, local community. Say what happened, or even our reservoir management, or how the gauge operated. Not only look at the data table or the shared drive document. And so, present your result to your peers or to some local residents to see, let's test and see what's going on and get a feedback, and even to your lab mate. And so that communication is very critical in this new world. Don't only bury yourself in front of a computer coding, although that's very important. And I did just to give a quick example. So I give a training, the generative AI for science training on campus. So that's the last training is 83% across the campus, people from plant science, from HPC, from Delta teaching instructor for engineering, from natural resources. But when I talk to them, I know their need. I understand their challenge. Even some basic thing, maybe I assume they know, or maybe they already know. We do not understand. That communication, face-to-face talk, and feedback is very critical. And because of that, and now I'm preparing two books because of that training. I understand their need. One of the book is how to build a small large language model step by step. So each chapter you can just have a Google Colab. You know where to download the data. You know how to clean the data, how the training specifically for generative AI. This is some other thing we are working. So I hope in the future, maybe hope for a couple of weeks, I can release these two documents. So each chapter, once again, because of this feedback, we know how the community need, how, what's the depth currently lacking of, in this field. So we can just adjust. So I think for the young generation, this is the communication, talk to your supervisor, talk to the local resident, talk to your peers. So even talk to your family member, what you are doing. Yeah.
Lindsay, did you have anything you wanted to add about sort of the importance of communication and collaboration when we're working through big data projects like this?
I was just looking at the time, so
It is about there, yeah.
gonna be quiet. I had one other point I just wanted to make as we close up, which is just thinking about like you leave here and you really want to, you know, encourage other people, like you want to do this more and you want to encourage others to, you know, maybe think about increasing their data skills and ability to do AI. And I just, one thing that we do so well as a community is peer review our publications and not peer review our code. So consider in a lab group looking at each other's code throughout a research project, not just the results that they're getting along the way, because you learn a lot that way. And it's kind of like a test as you go. So okay, that's the last thing I will add.
That's a really good tip. And I've definitely been guilty of keeping my code secret where like it's too messy, nobody can see it yet. And I feel like that really holds me back in terms of like this collaborative process. So I really appreciate that reminder.
So
Everyone
may I
has
add
messy
one more?
code.
May I add one more sentence? I think time management is very critical, not only for young generation, even my age. So try to use your time wisely. So young people are like, I know you like to play video games, but you know, if you want to really be excellent in this field, make sure you spend 1 to 2 hours in the coding or learning. I mean, you have to self-discipline. I mean, this is the key. No matter what you are doing, what you want to do in the future, if you cannot control your time, because time is very fair, but if you can control, will be multiply, you know, the effect of the time for you.
Thank you so much. And thank you to all of our panelists. It is a little bit after 2, so I want to be mindful of everyone's time. But I mean, Paul, Lindsay, I really appreciated all of your time. Thank you so much to CUAHSI for hosting us today for this conversation. And thank you all to the attendees. You asked some really insightful questions. I'm sorry we couldn't get to them all, but hopefully this was still helpful for everyone. I think that's it.
Thank you.
Thank you.
Thank you.
Thank you for yeah.
Thank you.
Thanks so much, everyone.